Welcome to this video on the Fourier transform and its application in speech recognition. The Fourier transform is a mathematical tool that converts a signal from the time domain into the frequency domain. In the time domain, we analyze signals as variations in amplitude over time. However, the frequency domain represents how much of each frequency exists in the signal. This transformation helps us break down complex audio signals, like speech, into their individual frequency components. Before we dive in, I'd like to remind you that all the Python code used in this video is available for download from the GitHub link in the description below. Additionally, you'll find a PDF in the repository that provides a step-by-step example of how to mathematically convert a signal from the time domain to the frequency domain. Feel free to explore the entire repository as you follow along or experiment with your own projects. Here is a visualization showing both the time domain signal, which is a combination of two sine waves with frequencies of 5 and 20, and its corresponding frequency domain signal. The frequency domain plot clearly reveals the dominant frequencies present in the time signal. What is remarkable is the simplicity of the information representation in the frequency domain compared to the time domain. While the time domain shows a complex waveform, the frequency domain condenses this into clear, distinct peaks, making it easier to identify and analyze the dominant components of the signal. In the frequency domain, the magnitude represents the total contribution of a specific frequency to the signal over the entire duration of the time domain signal. It is calculated by summing the amplitudes of that frequency from each moment in the time domain signal. In essence, the magnitude provides a measure of how strongly a particular frequency contributes to the overall signal, allowing us to identify dominant frequencies clearly and effectively. To demonstrate this, let us record a voice sample. We will use Python to capture audio and analyze its frequencies with a 5-second audio clip. The following code uses the sound device library to record audio. First, import the necessary libraries. Specify the sample rate as 44.1 kHz and the duration as 5 seconds. Then, record the audio, save it, and name the file recorded_audio.wav. Next, read the WAV file and use Matplotlib to visualize the time domain plot. This visualization shows how the amplitude of the audio signal varies over time, giving a clear representation of the recorded sound in the time domain. In speech recognition, the Fourier transform is used to analyze how frequencies change over time, which is critical for understanding spoken words. However, speech is not static, it changes dynamically as we speak. To capture this dynamic behavior, we use a technique called the short-time Fourier transform. This method divides the audio signal into small, overlapping time segments called windows and applies the Fourier transform to each segment. The displayed Python code performs this transformation and visualizes the result as a spectrogram. A spectrogram is a powerful tool for analyzing the evolution of frequencies over time. In this visualization, the horizontal axis represents time, the vertical axis represents frequency, and the color intensity represents the amplitude or energy at each frequency. This makes it possible to see how the different frequency components of speech vary dynamically, which is critical for understanding and processing spoken language. Building upon our understanding of how the Fourier transform and spectrograms help analyze dynamic changes in speech, we now introduce Mel-Frequency Cepstral Coefficients, or MFCCs. While the spectrogram provides a detailed representation of frequencies over time, it does not align well with how humans perceive sound. Human hearing is not equally sensitive to all frequencies, instead, it is more attuned to certain ranges. MFCCs address this by transforming the frequency domain data into a compact representation that reflects how humans perceive sound. This is achieved by mapping the frequencies onto the Mel scale, which mimics the logarithmic sensitivity of the human ear. MFCCs capture the most perceptually meaningful features of the audio signal, making them ideal for tasks like speech recognition and sentiment analysis. The displayed Python code converts the audio signal into MFCCs and visualizes them as a heat map. Each coefficient captures key characteristics of the sound over time, making them ideal inputs for advanced machine learning models. These MFCCs can be used as features to train deep learning architectures, such as convolutional neural networks, to perform speech recognition or even more complex tasks like speaker identification and emotion analysis. Be sure to subscribe to my channel and like this video to stay updated on related topics and future content. Thank you for watching.